Yeah. Good evening, everyone. My name is Aveen Dayal, and I'll be the live session TA for this course, Deep Learning for Computer Vision. And this is the live session 5. So, up until now, we've discussed about various concepts, starting from very first about what is an image. How do we represent the image? We can represent it using your traditional pixel wise representation, matrix representation, or we can also represent it as a function. And then we also talked about the most common operations that we typically do in image processing is like cross correlation and convolution operation. And then we talked about special operators like Sobel edge detector operators, which detects the edges. Then we also talked about operators, advanced operators like canny edge detector, blob detectors. And then finally, we discussed a very famous computer vision algorithm called SIFT, which will help identify the key features in an image, using which we can do several tasks like image stitching or object recognition, etc. So these were the first 2 weeks of the course, mostly about the traditional methodologies and techniques that were used in computer vision. Then from week 3, we started diving into the deep learning aspects. So we first discussed about the most fundamental and the simplest neural network, which is the perceptron. So we discussed what is a perceptron, how it trains, and then we further discussed about multi-layer perceptron, which are nothing but the new age neural networks or the deep learning networks. And we talked about different aspects of multi-layer perceptron, like how do we train it, like in forward pass, loss calculation. Then there is backward pass, which is nothing but back propagation. Then the process to update the weights or the parameters in the network is done with the help of something called as optimizers. And then we have gradient descent optimization strategy. We had mini batch gradient descent. Then we also have advanced optimizers like RMS prop, Adam optimizer, etc. We also discussed about various efficiency strategies which will help you during your training time, like regularizers, then dropout, batch normalization. Yeah, most of these techniques. Then we went into convolutional neural networks, which are uh, the most fundamental neural networks for image type of data. The main two reasons why it is better than the multi-layer perceptron is, one is it can preserve spatial invariance and by capturing the local features, and that also, and the other reason is the computational efficiency, since we have a small filter or kernel to be learned as opposed to the entire uh, weight matrix in the multi-layer perceptron or the node to node connection. So in convolution, the number of parameters are much smaller as to solve a typically simple image classification type of a task. So these are the two main reasons why convolution neural networks are best suited for computer vision, and why it is better than the multi-layer perceptron. Last week we discussed a bit more about what are these convolution neural networks, how do they actually operate in, like when you're doing the forward pass, backward pass. We also looked into some special convolution layers like pooling layers, max pool, average pool. Then we also saw about how do we calculate the output size, and we also did code walkthroughs. We did how do we build a convolution neural network using PyTorch. So coming to today's session, we will basically follow from there, and we will talk a bit more about is fundamental architectures of CNNs like ResNet, InceptionNet, MobileNet, EfficientNet, etc. And also we'll talk about strategies like fine tuning. So these ResNet or any fundamental architectures, these are usually built by larger community and the organization, and they usually train it on a huge data sets. So the advantage of these particular models is, if we ever want to solve a particular task, if any user wants to solve a particular task, they don't have to build such big models and train everything from scratch. They can basically take help of these existing pre-trained models, and then that can be like a very good starting point, and then they can fine tune or adapt to their particular use case. So that is the entire idea of transfer learning or fine tune. Okay, so that being said, let's first discuss the questions. So the format is the same like we had for other sessions, where we have in the first half of the live session we discuss a few MCQ fill in the blank type of questions, and then in the later half of the session we do the code walkthroughs of how we can write a code to implement the architecture itself in PyTorch. So this is the first question for today. So the question is the same, very similar question we actually solved last week. So it basically says we have an input image of the size 3 cross 64 cross 64, and we also have a filter of size 3 cross 5 cross 5, and there are three such filters. Now the stride of your convolution operation is 2, and there is no padding, zero padding. Then the question is, what is the size of the output of the filter? So maybe I'll quickly pause for a minute. You can try to solve, and you can post your answers in the chat. I'll just quickly pause for a few seconds. So here basically how we solve this particular problem is as follows. So we have the output size formula that we typically have, and this output size formula basically helps us figure out what should be the size of the particular convolution operations. So we have this simple formula which is nothing but w minus k plus 2p divided by s plus 1. So what are these different terms? Maybe let me write that down. So w corresponds to the width of the initial input image. K corresponds to the kernel which we have, that size. So typically kernels are square matrix. So square matrix is when we have the same dimensions. Like for example, typically kernel matrix is like x comma x, where x can be either 3, 5, 7, and 11. I haven't seen more than 11 typically. So these are the different possible values for x. Then p is nothing but the padding. S is nothing but stride. So given in our particular question, let me write down what is the values for our question. Width of the image is nothing but 64. The kernel size that is given is 3. We are given that the padding is 0 and the stride is 2. So if you just input all these values, we'll basically get the output. And this another thing to note, this particular operator over here, this is called a floor operator. So floor is nothing but it will fall if you have any decimal number. It will basically take the lower uh, part of the decimal number. So for what do I mean by that? Let's say I want to say floor of 10.5. It is nothing but 10. So you remove the decimal part and you pick the integer which is before that. So in this way, if we solve this problem, we basically get the output to be 3 cross 30 cross 30. Okay. Now let me go to the second problem. So in the second question, we basically, again, it's a simple fact-based question based on ResNet architectures. So you have the following four different statements, all related to a ResNet architecture. So I hope you've been watching the recorded lectures of the professor. uploaded by the professor. So based on the ResNet architecture, which of the following statements are so maybe you can take a guess about these four options. I'll quickly pause for a few seconds and then I'll explain how exactly or which of these particular options are correct or wrong. Let me explain the answers. So before explaining the options, let's first look at what are these ResNet models. So ResNet is nothing but one type of a very fundamental architecture which is built on CNN networks, CNN convolution operations basically. So what happens was, if you remember, we had the input image, then we had a bunch of convolution layers. Let me put it in blue. And then we flatten that convolution output, whichever you get, into a big vector. And then this vector is connected to an multi-layer perceptron. This could be of so many layers. And then we get our output vector finally. And this will be the output. So here in the blue color, where these are the different convolution layers that we have. So it could be n number of layers. So there is no restriction. It is a user design choice. So you can have 2 layers, 3 layers, 100 layers, even 150, 300, 400, whatever you want. It again depends on how much compute you can afford and everything. So when we have typically larger, or what we call in CNNs a deeper network, the problem what happens is during the backward pass. So what does a forward pass? Let's see. The forward pass goes through in this direction, calculates all the weight calculations like W into X, all these convolution operations, everything happens. And this is your forward pass. Then you calculate the loss using the forward pass and predicted value and the ground truth value. Then what we do is the backward pass, where from the loss we calculate the gradients, and these gradients are propagated. And how are these gradients propagated back? If you remember, we use the back propagation algorithm. In simple terms, it is nothing but multiplication of two gradients. So if at any point, if you want to pick what is this particular weight's gradient, it will nothing be, it will not, it will be nothing but the multiplication of all the gradients that were happening previously in very simple intuition terms. So usually, typically gradients are also very small values of the order something around very small values like 0.1. Sometimes it can be big also, but it can go up to 5 to 10 also. So now typically when the gradients are actually small values, and two small values when they're multiplied with each other, the resultant value will again be another small value. So it so happens that somewhere in between, right, the gradients after this point will be zero, because they've been multiplied so close to zero or almost zero, because they've been multiplying with all small values, it will become close to zero. So what happens is, because of these all gradient zero, all these layers, all these layers will not get updated. Their weights will not update. Now, if their weights are not updated, it technically means that the training has converged, right? That is what no weight update means. We are basically telling the model, don't update your weights, because whatever weight you have right now, that is good to solve the problem, because the loss is zero. That's why you're not getting any gradient from that particular loss. That is what it conveys. But that is not actually what is happening. The reason why it is becoming zero is because gradients are multiplied, small values are getting multiplied with each other, and that is why it is driving to zero. So to avoid this particular problem, which is called vanishing gradient. So this problem, what we solved just now, is called vanishing gradient. So to avoid this problem, people have come up with something called as a skip connections. In very simple terms, skip connections is nothing but a simple addition. It's just that. So let's say if I have convolution layer 1 and I do a bunch of other convolutions, let's say convolution layer 6. Then the output of convolution layer 6 and the output of convolution layer 1, these both are added and then sent to other layers, corresponding convolution layer 7 and so on. So now if the gradient is coming back, if the gradient comes from here, so gradient takes two parts. The gradient of course travels at this also. The gradient also travels to the top part. So now since it's traveling to the top part, if let's say for some reason the gradient over here is 0.1 and that's before reaching the top part, here it will become 0. It will still get gradient of 0. We are able to basically say that okay, now this particular value has some gradient and it is able to update the layers which were previously not getting updated because the gradients were 0. So this idea is nothing but the skip connections or residual connections. So if that is clear, now let's see and discuss each of the state. The first one says it employs skip connections. Exactly true. That is what the idea of ResNet entirely says. We need skip connections. It tackles vanishing and exploding gradient problems. It definitely tackles vanishing gradient problems. Think about if it travels exploding gradient problems or not. It definitely tackles vanishing. That's what I explained right. The third option says it works only for shallow, deep depth architectures, only for 2 to 3 layers, which is wrong because, like we just saw, it can work for any number of. In fact, it was created because the number of layers are more. Option D says using skip connections requires extra parameters, which is false because there's no parameter involved at all. You're just doing addition of the outputs. So there is no extra parameters. So the correct answers are A and B. That is the correct answers. So I hope this is clear. At any point, if there is any question, doubt, or something needs to be explained again, please let me know. So let's go to question B. Sorry, this is actually question 3, not question 2. Question 3 says, let's in inception nets, again another type of a popular neural net, just like ResNet. They have these concept of one cross one convolution layers. So the question says, what are the four statements that are true with respect to these one cross one convolution layers in inception? So again, let me quickly pause for a few seconds. If you can take a guess, and you can post your answers in the chat. Let's discuss the answers. So before that, let's discuss what is inception. Just like ResNet tried to solve a problem where of vanishing gradients, InceptionNet also tries to solve this, not solve a problem per se. It basically improves the existing way of how convolution neural networks work. So typically, they have these one cross one convolution networks. One cross one convolution networks. How it looks? Let's draw. This is your input image. Let's say this is typically kernel. We have 3 cross 3, normal average kernel size. Now, what will this 3 cross 3 see? So this will basically see 9 patch on the input image, which consists of 9 pixels, 3 on the column, 3 on the rows. Now let's go to the extreme case of 1 cross 1. So if it's just 1 cross 1, means it's just one element. So technically it will just see one pixel value. Okay. But you see the problem over here. One pixel value, what are we really capturing over here? The idea is we have to think of it in how the actual input image is. The input image is not two dimensional, it is three dimensional. So there is also the depth dimension. So 1 cross 1, the help of 1 cross 1, you can have number of channels increased quickly. So what do I mean by number of channels? If you remember the output of a convolution, what is the dimensions? It is number of filters you had, and then your convolution output size itself, con output size W, con H. So this number of filters, if you want to increase them, typically you start from initially input will be RGB image. You go from 3, then you go to 64, then you go to 128, 256, 512, and then you come back. You then vectorize them, and then you send to ML. So this 64, 128, 256, 512, these are the number of filters. So if you want to increase these filters without not having much of a computational cost, but at the same time, you're able to capture a lot of different features, because each feature, right, each filter that you're getting is capturing a unique feature, that not just unique, a different and better feature. So to increase these at the low cost of computation, one cross one convolutions help. So that is, let's now look at the options. First is to preserve local information. Not particularly, it does preserve local information, but not very helpful in this case. To keep the computational low, that is true. To have fewer parameters without degrading, that is again true. To enable faster sequential computations, not really. There's nothing about faster sequential computations. So the correct answers is basically B and C. So you can see A not particularly true because this is one pixel, not really local information. B again, there's no faster computations of sequential computations happening. All you are doing with one cross one is limiting the total number of parameters, which will inherently limit the computation cost without degrading the performance. So I hope this is clear. For the next question. So efficient nets are another type of more popular newer generation architectures. So the idea of efficient net was basically, I remember a lot of people in the initial class of CNNs also asking me, how do we decide how many number of convolution layers to have? How do we decide what should be the not filter sizes? Like, yeah, how do we decide what should be the number of filters to use after each convolution layers? So these are all the questions people usually have in mind when they're building their own architecture. And one option, of course, is you try a bunch of different values, and then you check the validation accuracy for all of these values, and you pick the one which is the most optimal one, or which is giving the best performance. But if you think about it, there are a lot of interlinked parameters, like number of filters depends on number of layers, etc. Even depends on the input size, also input resolution size. So efficient net paper, or the authors basically came up with a more formulated approach, and they came up with actual formula which basically says how much should you scale the number of filters, or the number of deeper layers you want to go, and the input resolutions, all of them correlates with each other, and they came up with this formula that can basically help you figure out what is the most optimal way when you're creating the neural network. So that is the typical idea. So maybe uh, try to answer that if you already know. If not, maybe I'll quickly pause for a second and we can discuss what exactly is that formula and how it is related with each other. The sorry, yeah, the dimensions and everything. Okay. Let me discuss efficient nets itself. Let's look at how it looks first. So typically there are four figures in this. The first figure is the baseline figure. So this is how you typically have a neural net. So you have your input resolution of the image, which is the height and width of the image. And then you have a number of layers. Each color block which you see, that is one convolution layer. And you can see after every convolution layer, your number of channels, which is the width, right? That is increasing. So in this particular efficient net paper, they have these terms where this is called the depth, this is called the width. So width in their sense is nothing but the number of channels you keep on building. Okay. And resolution, input, image resolution, that is input. So now if you they say that all these three things, width, depth, and input resolutions, can be related with each other. So if you want to scale the width, means you keep on increasing the number of channels. But till what extent? So typically, if you look at a convolution architecture, so you have that input image, then you in your convolution, like I said, you keep the input size keeps on reducing, and then it becomes one big vector. But like I just said, your number of filters keeps on increasing. It goes from 364, 128 to 56, 512. This is nothing but number of filters. So you're basically, as you go deeper, your resolution of the input image decreases, or the width and height of that convolution output decreases, but your number of filters increase. Now, why do we do this? What is the idea of this? Is basically we are basically saying that each filter captures a unique feature, or at least that's what we hope to capture. So we want at the end of the day a bunch of features which will be the most representative of this particular input image file. Now, if you don't reduce the height and width after each convolution, the number of filters, if you have 512 and still the same initial height and width, the computation will its cost will be very high. It will not be possible to calculate so many computations. So to make it efficient, and at the same time to, because we're anyways, each convolution effectively what it will see. So if you think about it, each output over here is looking at a patch. Now this entire, again, this big output is one patch, and similarly this one is another patch. So you're effectively still looking at that like a telescopic view, we call it basically. So you can still see that telescopically you're looking at a bigger patch, but now across the number of channels you're able to capture different features in these different patches basically. So that is what we want to achieve. So that is why we basically do the scaling, width scale and depth scaling. That is a motivation. So option 2, you see, width scaling is nothing but increasing the number of channels, making it wider and wider. Depth scaling is when you want to go deeper and deeper. Resolution scaling is if you want the initial resolution to be high. Why do we need that? We all know that higher resolution pictures or higher resolution input is always better. You'll see a lot more you'll get a lot more information capture. Low resolution images have much more like pixelated images, right? Which we see, those are low resolution images. But again, that comes with a computational cost trade-off. So this option E is what they call the compound scaling, where all of these three things are correlated with each other through a particular formulation. That is the compound scaling, which is efficient nets formulation. So now based on these efficient net idea, let's go back and look at the questions. First, it says it relies on compound scaling of depth, width, and resolution of architectures. True, that's what I just discussed. The general principle of model scaling can also be applied to mobile nets and REST nets. So this is absolutely true. So efficient net is built. The idea of efficient nets was basically you take any CNN architecture, how do base architecture, and how do we make it that efficient by adding how many layers around. So ResNet is doing a different thing. ResNet is basically having that residual connections. It has nothing about intervening about the scaling of the architecture. So all of these architectures, ResNet, MobileNet, InceptionNet, they all can also have the same formulation proposed by efficient to identify what is the most optimal depth and width of their particular family of algorithms. So option B is true. Option C says it helps design architectures that achieve maximum accuracy under a given budget of resource constraints. That is again true. That's what we are saying. The idea is, let's say I have 32 GB GPU. Okay, there is only a limit how big of a model I can train on this 32 GB GPU. So it is very important to most effectively use these 32 GB GPU. So that is what this particular efficient net is saying. So maybe instead of you having 100 layers, deeper layers, have 50 but have much wider and bigger resolution. So then you can effectively still use the same resources which you have, but now get a much better accuracy. So that is option C is true. Option D says it takes long time to train. So there is no empirical evidence that suggests that efficient nets have longer time to train. Maybe in certain cases, very rare, I haven't seen that, but it's very unlikely. It's not at all a true state. So the correct answers are A, B, C. So if this is clear, let's move ahead to the next question. So the question is very simple. It says, can deconvolution method be applied to ResNets? It's a simple yes or no question. So deconvolution is nothing but the reverse of convolution, or transpose convolution, if you want to. So can the reverse of convolution be applied? Method can be applied to ResNet type of architecture. Maybe you can take a guess. Any simple yes or no. So maybe let's see what is a deconvolution first. And so the answer is yes, it can be applied. So deconvolution is nothing but this, what you're seeing. So what does convolution do? Convolution looks at patch, calculates the output, and this is going, this element, one output element is looking at this patch of the input. Deconvolution is the opposite. You are given a smaller matrix and you have to take each pixel and project it into a bigger image patch. So where do we typically use this? You have not come across it yet, but this particular deconvolution operation is very important in something called as segmentation models. You will see in the late, most likely in week 7 or week 6. Segmentation is a particular type of a computer vision task, and for those you would want to use these deconvolutions. So typically when you are using a deconvolution, your architecture looks like this. You have your input image I, you have a bunch of convolution. Like I said, it keeps on reducing the size until you come to reach a particular small size. Now then you apply deconvolution and you increase the size in a similar manner until it gets to the same size as the input image I. So the first half of the operation is downsampling. So downsampling is nothing but another word when we're reducing the size of the resolution of the input images or inputs. And then the later half is basically the upsampling. Upsampling, just another word for increasing the inputs resolution. And this downsampling is done by your standard convolution operators. The upsampling is typically done by your deconvolution operators. So deconvolution, another popular name for that is transpose convolution. So if someone says transpose or it means nothing but deconvolution. Someone says deconvolution, nothing but transpose. So yeah, so ResNet, what it does a typical convolution, but it has no restriction that you can't use the same ResNet ideas in deconvolution. ResNet is nothing but it's additions, right? You're just adding. So if you think what was ResNet, it says that okay, take this, add here. Similarly, you can during deconvolution also you can take from here, add here, or you can even do something which is one of the popular algorithms. You take from first half of the layer, add to the second half of the layer. So you can do anything. So typically, ResNet type of residual connections can work even in deconvolution stage. So the correct answer is yes, we can have deconvolution methods in ResNet architectures too. Uh, I hope that is clear. Now let's move ahead to this final question in the MCQ part of this session. So here we have three architectures: ResNet, MobileNet, EfficientNet. They all of them are designed to optimize performance, accuracy, and efficiency, computational efficiency. Given we have to perform a complex visual task that requires fine tuning these pre trained networks on domain specific data set, or a given data set, you can think. Which of the following statements correctly explain the trade offs involved in selecting the architecture and the fine tuning strategy? So these are the four options. Maybe this is a slightly bigger option, which have like big sentences in the option. Maybe I'll quickly pause for a minute. Take your time to read, and then I'll explain what it even means, and we can discuss each of the options. So let's discuss. Firstly, we have to discuss what is even fine tuning. Forget about the options for now. Let's see what does even fine tuning mean. Okay. So typically we have convolution architecture, whatever it is, ResNet, whatever it is. So you take this convolution, you take this architecture, you have a big data set. I will show you in today's class what type of a data sets are like these big data sets. You take this convolution architecture, maybe let's have some example also. Let's say we have ResNet. We have ResNet 101. That means it has 101 layers. We take this ResNet 101, you train it on this very big data set. So typically these big data sets, what should be the quality of this big data set? It should be a general data set. Like means like what do I mean by general? It should try to cover uh, different objects that are there in the real world, typically that people see in the real world. And at the same time, the number of objects should also be big. Okay, it should be big. So once this you take this ResNet model, you train it on this big data set. We call this uh, number one. This is called the pre-training part. What is pre-training? ResNet plus trained on that. What plus means trained basically trained on that big data set. So usually this pre-training is complex because it is a very big data set, very big architecture, and you're training everything from scratch. So it takes a lot of compute, time, everything to do this thing. So we'll write over here compute cost high. Now let's say you have your but now let's say a user typical user has a very small use case, okay, small data set for that particular use case, whatever he wants to solve. Like maybe he just wants to predict whether uh, there is a dog or a cat, like a small only animals detection type of a task he has, not like a very big task. Not even all animals, just like dogs, cats, and birds. That's it. So what can he do? He can he has two options. Let's write that options down. Option number one: build a small CNN. Build small CNN. When I say small, it could typically maybe be around like 10 to 50 layers. That is also not small, but let's say We're calling that small. Build small CNN plus means train that on that small data set from scratch. Or option two, you take the ResNet 101 from the pre-training. So we take retrained ResNet. And then you train it on the small data set. So when we do the second, where we have this small option two, where we take this ResNet, pre-trained ResNet, and then we train it on this small data set, the advantage over here is you, let me write the advantage on the top. Your starting point is very good because the starting point, the start, when I mean the starting point, it means the weights, the starting weights. Typically, if it's a option one means random weights, right? So obviously, the starting weights in option two will be very good because it's coming from a pre-trained ResNet. Whereas in option one, the starting weights will be bad because it is random. So now, why does the starting weights matter? Because if the starting weights are already pretty good, the overall time that it takes to train this on this small data set, it depends on how well you get arrive at the very good weights for these tasks, right? So if the starting weights are pretty good starting point, you'll reach at the optimum point in a faster time compared to the option one, which might take a lot more time to converge. So this is why. So option two is nothing but fine tuning. So this is called fine tuning, and another word for this particular type of training strategy is called transfer learning. Why is it called transfer learning? So as you can see, oh, sorry, as you can see, we're basically transferring our knowledge from a pre-trained model to another particular small use case. So that is why it is called as transfer learning. Okay, so if this idea of fine tuning is good and clear, now let's go back and look at what are the options. First option says when fine tuning a deep ResNet model, utilizing deeper residual blocks introduces a bottleneck in gradient flow during backpropagation, even with skip connections, thus requiring the modification of residual connections for effective learning. This is not a correct statement because the entire idea of skip connections or residual blocks was because it will help the gradient flow more efficiently. That is why it came into picture. So there is not the statement is false because this there will be no gradient bottleneck because of introducing residual blocks. So this option A is false. So option B, let me skip for now. I'll explain first what is mobile net and then I'll come back to option B. Now let's go to option C. Option C says efficient nets compound scaling makes it less sensitive to the downstream dataset size during fine tuning because it evenly scales width, depth, resolution, resulting in consistent improvements. This is exactly true. This is what we are doing in fine tuning, that we are downstreaming or we're transferring the knowledge to a smaller task. An efficient net basically says how can we effectively come up with a optimal model given a particular resource constraint. So option C is true. Option D says fine-tuning any of these architectures involves reinitializing the entire network as it allows for greater convergence speed and eliminates the risk of overfitting the pre-trained weights to the new dataset. So this is again wrong. It's the opposite of what the objective or the idea of fine-tuning is. In fact, it doesn't reinitialize the entire network. Firstly, it starts from an already pre-trained network, and it uh, if you're doing fine tuning, then it will have a faster convergence speed, not by randomly initializing the net. So option D is wrong. Now let's look at what is a mobile net and then we can come back to option B. So mobile net has three versions till now. So I'll explain maybe the version one, version two. and version 3 you can always go through it in your own time. But idea of version 1, why it was helpful, or so first let's discuss why is it called mobile net. So the name mobile net, like it suggests, it is models that can be easily deployed on mobile or small devices like edge devices or mobile devices or any constrained device. So that is why they're calling it mobile net, because they want to deploy it on smaller mobile devices. Now, how do they propose making these operations smaller or computations smaller? Is by proposing something called as depth convolution. So a typical convolution, if you remember, so in the aspect of three dimensions, let's say I have a small kernel. So this I'm just drawing the kernel over here again. So this kernel basically traverses across this input volume block. So we do what in this convolution when each of this block is kept on each input image patch? We basically do element wise multiplication and calculation. So this is typically like if we call this k cross k, okay, and the entire image is like m cross n, and let's say how many filters we want. Just for one, we have n number of filters to do. Okay, let's say we have total uh, capital F. So the number of operations that happen over here is k into m into n into s. Okay, this is typically how much a convolution computation happens. But now, if you look at what depth-wise convolution says, depth-wise says ki don't do the convolution across the entire depth of the input, but do convolution separately for each channel in that input. So you can see that you have like four channels over here, five channels over here in the input, and we are doing separately first a simple two-dimensional convolution across each of these channels. So you can see first the blue depth-wise convolution happens. Please mute yourself. In- So here in depth-wise, so first we see that depth-wise convolution, it takes each kernel 2D convolution it does on channel 1, channel 2, and so on up to channel 5. And each of these output is saved. Now you combine all of these outputs, then we basically do a summation, which is nothing but the one cross one convolution. Not summation, sorry. We basically then have the capital F number of filters over here in this one cross one convolution, and that is your final output. So we're basically splitting that convolution typical process into two parts. One is depth-wise convolution, one is point-wise convolution. So let me write it down. In depth-wise convolution, you pick one filter and you do this depth-wise convolution. In point-wise, you have capital F number of filters. So now typically your computation will look something like this. K cross K cross M cross N into 1 plus F. Something approximately like this. I might be missing out a few terms, but approximately you get the overall computation to be this. So we save a lot of computation by doing in this depth-wise convolution manner. So that is the novelty that was proposed by MobileNet version 1. MobileNet version 2 then proposes something called as their inverted residual blocks, where they say if the input has 24 channels, let's first project it into higher dimension space. That is, what is that higher dimension space? You increase the number of channels. So you expand the number of channels to 144. In this 144 space, you do a depthwise convolution, because since it is an efficient way to do convolution, it is okay that you're doing in a higher dimensional space here. Once you're done with that convolution, then you project it back to the original dimensions. So the again the intuition of doing this is, we typically have this idea usually in machine learning also, that data that is not separable in smaller dimensions, when it gets projected into higher dimensions, it can be separable. So think of the same intuition, but in terms of convolution operators. The number of channels is nothing but the effective features. Features which might not be very clearly separated in smaller number of channels. If you increase the number of channels, those features can now clearly be separated from each other. Then you do the feature extraction, that is nothing but this depth-wise convolution, and then you again come back, project is back to the lower dimension. So that is what MobileNet version 2 proposes. Okay. So now with these two versions, let's go back to option B. Option B says fine tuning MobileNet on a new task can leverage the model's highly compressed architecture, but may result in a greater drop in accuracy due to its aggressive parameter reduction. This statement is false, because MobileNet entirely was proposed because it is able to reduce the parameters drastically, but at the same time maintain the accuracy. So it's a trade-off. We don't want to build efficient architectures with less number of parameters, but those are not performing well. We want to perform well at the same time have efficient parameter architecture. So option B is also wrong. So the correct option is only option C. Okay. Any doubts or any clarifications or anything uh, for any of the concepts which we discussed in today's class? Okay. If there are no questions, let me then go to the code walkthroughs. I hope everyone got the time to look at the previous collab notebooks which I have shared. So I hope you were able to figure out what is a PyTorch, what can you do with PyTorch. Like you can create different tensors, you can do a lot of tensor operations, like uh, the basic ones like adding, subtracting. Those are the standard ones. Apart from that, you can do matrix multiplication type of operations. You can also create new tensors like from random distributions like normal distribution, uniform distribution, and then etc. And we also saw in the last two sessions how we can create neural networks in PyTorch. We saw two different ways. One was using sequential module, where you tell the neural network, okay, these are all the layers I have. You tell PyTorch, these are all the layers I have. You keep it in in a list kind of a thing and give it to PyTorch. So whenever input comes, it will automatically send it to this list of layers and it'll give you the output as the answer. Another option is, we a user manually writes the code where he or she takes that input from input and sends it to layer 1, take the output of layer 1, sends that as an input to layer 2, and so on up until the final output is achieved. So these are the two typical options that you can use in creating the neural network. Each of them has their advantages. If you already know what are the layers and you don't really need intermediate outputs, you can use sequential. But if somewhere you want intermediate outputs for more customization, it's better to go the other way around. And sometimes you can use both also. Typically, some blocks you can keep sequential, some blocks you can get the output of that and then send it as an input manually. That also you can. Okay. And then we also saw, in the last week, how you can load your image data sets, how what is the data loader and everything, and how can you create those batches. We also saw how to train your neural network in an efficient manner. It's simple step. It's the four-step process to train your neural network using PyTorch. But those four steps are very important to understand. And we also saw the loss functions and everything. Today we'll again see the same concept, but we'll create a actual ResNet architecture. So we'll first see how you can train your own architecture of ResNet, what you created from scratch. We will also see how we can do a fine tuning strategy, that is transfer learning for this for a pre-trained ResNet model. Okay. So first things first, like I always suggest and tell, have your import statements ready in your starting of the code. Typically, in when you're writing a script, so there are two parts. There are two ways to write any code. You can write full scripts where it usually have the extension .py file, where you write your entire code block, your entire code in one script, and you run that particular script either through command or through GUI. Another one is notebooks, where you have small code blocks like these, and you run typically each of these code blocks separately. So when you're running this code block one, the below code will not get executed. Only this particular code blocks gets executed, and it gives the out. So first you have your import statements. So since it's just a second class for PyTorch, I'll again go through what are these import statements. First is import torch. This is nothing but you're importing PyTorch library itself. The second is there's something called as torch.utils.date. So this basically helps this particular library or module has a lot of helper functions that you can use for handling the data, input data. From this, we're importing something called a sample. We'll see what it is. Import torch vision. So as the name suggests, this is the library of the PyTorch that handles all the vision aspects, the data sets, the pre-processing of the images you want to do, all the popular image data sets that are out there. It can also be uploaded inside this library. Next is we are importing something called as a data sets from Torch Vision. Data sets is a structure, just like how array is a structure, list is a structure, dictionary is a structure. Data set is another structure where PyTorch expects all your custom data. If you ever want to upload your own custom data, it expects that they inherit or they follow the same template that is written by these data sets class, which is there in PyTorch, in Torch Vision. Then next we have data loader. So data loader is helpful for creating the mini batches, because like we all know that big networks, neural networks, they are not trained in full batch gradient update, because that is a very costly and resource extensive process. Instead, we do mini batch gradient update. So how do we create those mini batches? How do we load that mini batch from our secondary memory to the RAM for the for the neural network to see? And once that is computed, it has to again go back to the secondary memory. All those things are handled by data. Then we have another helper function called subset random sampler, which we will see how where we can use. So it's like the name suggests, you're basically sampling randomly a subset of data, but we'll see how we can use it. Next, we have transforms. So transforms, we saw last time also. Whenever we want to do pre-processing of our input data, we use transforms function or a class basically. So transforms can basically transform your input data or pre-process your input data before sending it as an input to the neural network. We can do a lot of operations like uh, you know rotating your image, brightening your image, adding noise to your image, converting the image to a tensor. That is very important. Then also normalizing the image, etc. Then we have other basic import OSs, Python's way of interacting with the operating system. NumPy is another library, very important. Just like tensors are there in PyTorch, NumPy has something called arrays. Then import random, it basically helps in creating random distributions, random values. Then versioning, you can just forget for now, it's not important. All of the iter tools, time, these are not very helpful. What is again important is matplotlib. This is a library that uses or that helps you to visualize plots. Not just plots, plots like scatter plot, line plot, bar plot, but it also helps in visualizing the images too, not just typical plots. Uh, that being said, let's first see what are the help. First, we have helper functions for data load. So this is a normalize or unnormalized in this case. So typically you're given normalized input, and unnormalized is basically you multiply with standard deviation and you add it with the mean. So to normalize something, you basically subtract the mean and divide by standard deviation. The unnormalized is the opposite, where you multiply with standard deviation and you add with the mean. So that is what we're doing. So then we first create MNIST dataset. So let me show the MNIST dataset first. Okay. So I think we have a sample for that. Okay, let me explain what is this. So MNIST dataset, again, it's a very widely used, a very popular dataset. It consists of handwritten digits from 0 to 9. It consists around 50,000 data samples. There are 10 classes, digit 0, digit 1, so and so up to digit 9. And each of this image is nothing but a handwritten image of a particular digit. So that is what your MNIST dataset. So here we first create a data loader function. So data loaders, how we can create for this MNIST dataset. So typically, like I said, transforms is basically helps you create transform your data. So here one important transform you always need to have. If not anything, this is definitely must, because every image by default is not a tensor, and PyTorch only takes tensors as an input. So you need to always convert. You have to have a transform called dot to tensor. This will convert the uh, input image into a tensor. If you don't do this, you'll get an error. It says that okay, the input is not a tensor. So it's always must. You have to have this transform dot tensor. So that's why I'm saying if train transforms is none, at least you have the default transform, which is two tensor. Similarly for test also, if you have no transformations to be done on the test data, but the bare minimum transformation you need to do is two tensor. Okay. So first thing, we have to load the data sets. So luckily MNIST, like I said, it's a popular data set. It is already present in PyTorch. So that's why we just use this datasets library and say datasets.mnist. So we are basically calling that MNIST data which is there in PyTorch, and we mention few arguments like root is where should we download the data, train, whether we want the train split of the data or whether we want the test split of the data. Transform is basically we mention what are the different pre-processing that needs to be done on this data set. Finally, we say download equals to true. Then we have validation data set. Again, if we remember, validation comes from train data set. Right? That's why we keep train is equals to true. Then finally, test data set. Here we put train is equals to false. It says, okay, this is the test split of the MNIST data set. So now we have to first create the validation data set. So here, if you see these two train data set and valid data set, the number of samples are pretty much the same because we are using the train equals to true in both these. But we need to create a subset from this. So that is where the validation split, the samplers which we saw, right, helper functions, that will come into play. So you first want to identify what is the fraction of the original data you want to create as validation. Typically 10%, 15%, the most 20%, not more than that. So the fraction will be 0.1, 0.15 or 0.60,000 is the overall data size. So out of 60,000, we pick 20% of whatever the fraction is mentioned as the validation set. So that's what we're showing over here. So train indices will be uh, everything. So in that 60,000, the first, let's say 58,000 is train data. So the first 58,000 will be train indices. The remaining 2,000 will be validation indices. Now you take these train indices and validation indices and you give it to something called a subset random sampler. So subset random sampler basically picks randomly a subset from this entire indices that is given, this list of numbers. It picks randomly a subset of numbers. And these subset of numbers will basically identify what are the data samples that have to be given. Now, let's say after you create the samplers, now you have to actually load the data. That is where the data loader comes into picture. So data loader takes few standard arguments. So the first argument that the data loader will take is what is the data set itself. So here we are saying, okay, first is the validation data set. What should be the batch size? This is the parameter, again, hyperparameter. You have to decide based on your GPU availability. If you have big GPUs, go for bigger batch sizes. If you have small GPUs, go for small batch sizes. Next, we have number of workers. Maybe let me keep it more interactive. Any guesses? What does this number of workers do? You can take any guess. You can post your answers in the chat. Why do we need this number of workers and how does it help? Okay, so number of workers basically tells how many processes in Python it has to create whenever data loader is evoked. Let me tell in simpler statements. What is the job of data loader? Data loader's job is load the mini batch from the secondary memory, send it to the RAM. Now you can have one particular process or worker to take that to do that, take it from secondary to RAM and vice versa from RAM to secondary, or you can have more number of workers to make the process faster. So number of workers, if you have more number, it will create more workers or processes to do this loading and unloading of mini batches from secondary to RAM much faster. But of course, there is a limit up to which that can happen. You can't just infinitely do that. It depends on your system, what system you have also. So that is what number of workers help. Sampler is basically the sampler which you just said. We pick the random sampler subset of this random. Similarly, we create a train loader also. This, if you want to create a validation split. Sometimes we really don't want to create a validation split. Very unlikely. Most likely we want. Otherwise, if you don't want to, just create a train data loader as it is. And then we, if you're not using a subset random sampler, you need to use something called as a shuffle equal to true. Again, any guesses? Why do we have to keep shuffle equals to true when we are sending the training data to the neural network? Any guesses? What do you think is that shuffle equals to true? You can understand that shuffle equals to true means it is shuffling the input training data before sending to the neural network. But why do we do that? What is the advantage or what will happen if we don't do it? Okay. So the advantage of shuffle equals to true is typically a neural network updates, we all know it, mini batch. Like it will see probably, let's say, 32 samples at a time. It updates the weight. Now, if it's not shuffled, you will probably see in the 32 samples all of them belonging to one class. So when the model is updating, it doesn't know that what are the other classes that is there because it is just looking at this 32 and updating. If all of them belong to the same class, it will think only this class is present in the data set and it will do a wrong gradient update. And in the next 32, it will see another class and again it will go into another wrong direction and it keeps on jumping up and down until it reaches the optimal point. So to avoid that, it is preferred to shuffle your data as much as possible because when we do that, the 32 samples which are there in the mini batch, they will come from diverse classes and the model will see kind of like almost the entire representation of your original data. That is the goal over here. It is not necessary that all the classes will be covered in a mini batch, but at least a diversity is maintained. So that is why it is important to have shuffle equals to true. In test, it doesn't matter because we are not updating the model. So you send all classes, one class, or only one type of class doesn't matter because you're not updating the model. Okay. So this if condition basically, if you have validation split, you send three. If you don't have validation split, you send two loaders. If you have validation split, you send three loaders. Now there's other data set called CIFAR. Now this is a bigger data set than MNIST. So CIFAR 10, um, I'm not sure the organization that created. Yeah, CIFAR 10 was created by Jeffrey Hinton's organization, the person who won Nobel Prize recently. So uh, that's what I believe. Might be wrong. We can check again. But what is the idea of this data set is it has 10 different classes. There are two versions. There is 110 class version. There's 100 class version. So they capture a lot of common objects that are present in the real world, and they try to not just objects like anything that you see most relevant in real world. Those are basically captured and kept as classes. So it's a huge data set which captures different diverse commonly appearing classes which people typically encounter. So now the goal was to if you train the model on these data set, the model should do well at a more generic type of tasks that a human wants it to do. Okay. Same concept, same whatever we did for MNIST also, we do the same way. We first check if there are any train transform test transform. If not, give the default two tensor transform. Again, CIFAR10 is also available on PyTorch. You can just load that datasets.cifar10. We again do the same subset sampler which we just saw, which creates for if we have a validation split, it creates a random sample for that, and we return based on whatever is the if condition. Now let's come to some more helper functions. First is setting all the seeds. I've explained this previously also. Very important. Why do we need to set all the seeds? Because we want to ensure reproducibility of our experiments. Because all of the neural networks, the entire pipeline, right from picking which mini batch to send to the neural network to transforming each input image before going into neural network to randomly creating your neural network weights and updating the model. All of them, this entire pipeline has a lot of randomness in the background. So if you don't set the seed, what happens is my randomness, because it's in random, right? My instance of that random distribution will be different from your instance of that random distribution. You're as in anyone who's trying to reproduce the results. Now, because of that, if the accuracy which I get will not be the same accuracy which you will get to the exact decimal point, you might get plus or minus 2, 3, 4% difference also. That is problematic because if I'm reporting in a research paper or in a production saying, like for a company saying, "Okay, this is the accuracy I'm getting," they should ideally expect that accuracy when they're actually using it. It's not like they'll get a different accuracy when they're using for their in their particular GPUs. And so to avoid all these confusion, set your seed. Once you set your seed, all of the reproducibility will be ensured. All of the randomness, while it is still random, if I set something like set seed is 42, even if it is randomly initializing everything, every 42 will be initialized in the same random way. So that is what is happening when you set the seed. Set deterministic is the same thing like set seed, but here we do it when for GPUs basically. So GPUs have this library called CUDA, which basically helps PyTorch talk with the GPUs which is installed in the system. So they also have certain randomness. So we have to set their seeds also in a similar way, like how we set a seed. Here we set some flags basically, which we call deterministic flags. And these are some simple functions to calculate accuracy. I will not discuss this in detail, like standard functions, nothing about neural networks in this. You just look at predicted and the ground truth and are they the same or not. If yes, you increase the number of correct variable to be one plus one. And you finally accuracy is number of totally all the correct values divided by total number of samples. Confusion matrix is another evaluation metric. where it will try to identify all the true positive, false positive, true negative, false negatives, and it will be using which you can create your precision recall F1 score. And in the interest of time, I'll skip this. Let me go to the main part. So train model is the function using which the model actually trains. So train model typically has two for loops. The first for loop, outer for loop, is the epoch for loop. So like I said, the epoch is nothing but when your model sees the entire data set once and updates. That is when we say one epoch has completed. But we can't update an entire data set together because the data sets are huge and the GPU RAM is small. That's why we do mini batch update. So the inner for loop is where you load each mini batch, you update the model, and once all of the mini batches are loaded and unloaded, then one epoch is complete. Then you repeat this entire process for n number of epochs. So that's what we do. We first have the epoch for loop, then we say model.train, which basically tells PyTorch, okay, my model is now in the training phase. You also have model.eval, which will tell PyTorch the model is in the eval phase. So in the mini batch for loop, we first get the features and targets. This is nothing but the inputs. Targets is nothing but the ground truths. Then we send the inputs, which is nothing but the features, to the model. I'll explain what the model is. For now, you can treat it like a black box. Just assume that this model is taking an input. It'll take an input. That is what is features. Output is nothing but the logits. Then you send this to a loss function, which is cross entropy loss, very standard loss. Cross entropy loss takes logits and targets as an input. Targets is the ground. We get the loss. Now, before calculating the gradients, we have to first zero out the gradients from the previous update. That is what this optimizer.zero grad does. If you don't write this line, your model will confuse and with the previous gradients, the current gradients, and the update will happen in a very weird fashion, and the accuracies will be very. Always make sure and remember to have zero grad written in the for loop before you calculate the loss dot back. So first you zero out the gradients from the previous update, then you do loss dot backwards. This loss dot backwards is where the gradients for this particular step is calculated. After that, we do optimizer dot step where the model updates all the parameters. That's it. These simple four steps is where the training happens. Apart from that, you can do some logging of the losses, train loss accuracy, train accuracy. And then after every epoch, we also want to calculate the validation loss and validation accuracy. That's why this model.eval is outside the inner for loop. It's inside the epoch for loop. So after every epoch, we set our model into eval mode. We calculate the validation accuracy and we print that. We store that values. That's it. So there are some schedulers also. So schedulers basically keeps track a lot of what is the uh, at what point of time you want to log the values and everything. It can also be used into updating the learning rates also. Schedulers is basically an entire different concept. You can look into it your own time, but typically it basically identifies what is the schedule in which the training is happening, and after every few steps of input steps, you can basically define different parameters to work differently. So then these are some plot helper functions using which you can plot the training loss and test accuracy and everything. I'll just quickly move ahead. Again, show examples will basically for some samples we'll show how is the model's output looking for that particular input sample. Let's go to the actual model itself. Okay, so here we create now ResNet 34 model on CIFAR10 dataset. We first set the random seed. Okay, I want these values. Batch size is 256. Number of epochs I'm setting. Device is important. It always have this code written torch.device CUDA 0 if torch.CUDA is available. It basically says if your computer is GPU enabled, that will say it will store that in the parameter device variable device. If it's not, the variable device will be CPU. Always have GPU when you're training neural networks. Otherwise, it will take days, months, also sometimes to train these big models if you're using CPUs. Then we first call to set all the seeds, which we just saw the function which we just created. We'll set all the seeds based on this random seed. Now, these are some standard transformations that you want to do for the CFAR 10 images. What are we doing? We first resize the input image to 120 cross 120. Then uh, we randomly crop 110, 110 from that 120. So basically 10 pixel values are removed. Then we have two tensor. Basically, we're converting our particular input image to a tensor. Then we normalize it using these. Since it's three channels, right? We have three means: 0 0.5, 0 0.5, 0 0.5, three standard deviations: 0 0.5, 0 0.5, 0. The same similar we transformations we have for test also. And now that function which we wrote, get data loaders for CFAR, we basically send the batch size. We say, okay, I want 10% of the training data to be validation. That is what is the val function. Then what are the transforms and number of workers. So let's look at uh, the images. Let's look at what are the input shapes which we got. So we loaded the data set and everything. Image now has this batch has 256 is the number of samples in a batch. 3 is the number of channels in the image. 110, 110 is the image size. Labels is nothing but it's a single number, right? So it's just 256 values. Each value is nothing but an integer. So these are the 10 different uh, classes starting from 0 to 9. So you have 10 different classes. Now, what are the classes in CFAR10? You have something like aeroplane, bike, person, etc. Some common appearing things. Now let's go to the model itself. So we first so typically, yes, what we saw last time, we created directly a small class called ResNet, and then we created 2, 3 layers. But not ResNet, we called AlexNet, and we created 4, 5 layers in that AlexNet using convolution operators. But when we have to create bigger and bigger networks like 34, 100, 250 layers, what we do is we create functions of each operations. Like 3 cross 3 convolution is an operation, 1 cross 1 convolution is an operation. So we create these functions and then we keep a for loop and call these functions repeatedly. So instead of us writing 3400 times, we just write in a for loop, and that for loop will call these functions and create those layers. So that is what we're doing over here. So we first create two fundamental convolution operations. First is 3 cross 3. How do we create that? We use torch.nn.conv2d. So this is the command get to create a convolution 2D layer. Input in planes is nothing but the what is the input filters that is coming to this convolution layer. Out planes is how many number of output filters you want after the convolution. Kernel size, what is the kernel size? Since it's 3 cross 3, it's just 3. Then stride, padding, etc. You all mention. Similarly, for 1 cross 1 also, we create the same command with their corresponding arguments. Then we first create something called as a basic block. Again, 32 layers consist of blocks inside them. So we first create one block. We repeat this one block such that overall number of layers will be 34. So this basic block is again a neural network block. So that's why we are inheriting very important. We always inherit the nn.module. It tells PyTorch that this particular class is a neural network. And we have two, whenever you're importing or creating neural network, you have two functions: init function, forward function. There are other functions also, but you don't care about those functions. All you care about is the init function and the forward function. Init function basically creates all the initial, what are the different layers you want, all that information it creates. So like for example, here it checks you have batch normalization layer. Do we want that in the if condition? Do we check if only basic blocks are supported or group blocks are supported? We also check if dilated convolutions. These are all different parameters. After that, we create the instance of that function con 3 cross 3 which we just created. Then we also have norm layers, batch normalization layers, ReLU functions. All of these important layers we create an init function. Forward function is where now we write how the input is going to each layer and how is that output of that layer going to the next layer. So that is what this input output game is for in the forward function. This is where the residual connection also happens. So first we are storing the input x into some temporary variable identity. Now we send this x to the first layer, get the output, send it to the second layer, get that output. Since it's an identity connection, we add the output of the second layer to the input identity. So that is output plus identity. This is the residual connection. That's it. Nothing much. We're just adding the output after second layer to the original input. Once you do that, whatever is the after the addition comes out, that will go as a final output. And because of this simple addition thing, people were able to stabilize the gradients. That vanishing gradient problem was stabilized. Now we create another block called bottleneck block. Same way, again we have to import that this is a neural network and end block. And here we have a bunch of different layers which we just defined. And again, it also has a forward function which it says what should be the input output, and it also has some identity connections. Now let's create the actual ResNet class, which will basically use all the other above classes and functions which we just create. So here, what do we have? We basically, I'll show you the main parts. Some simple convolution layers we still need. We created that. Self.make layer is where we are basically creating those particular instance of the blocks which we just created, right? Those will happen at the make layers. So these are the bottleneck block and the basic block which we just created. So here torch.init basically torch.init.came in normal. This says what type of an initialization to do. Like uh, timing normal is one type of random weight initialization. There are other ways also possible. So make layer is basically it takes each layer, like I said, the for loop, right? It takes the output from one layer, creates the input from one layer, and keeps on doing for n number of blocks and everything. So once you create those functionalities, all you have to do is another forward function for the main ResNet class, where you have the first convolution, send it to layer 1, layer 2, layer 3, layer 4. Each of these layers have their bottleneck blocks, residual blocks, and all the outputs will be first converted into a vector. That is what this average pool is doing. Then you send it, oh sorry, not the average. Torch.flatten basically converts it into a vector. Then you send it to the fully connected layer. And finally, you get the output from the ResNet. That's it. So here we create the instance of the ResNet block which we just created. We want how many layers, what are the each values in these layers we want, we specify. We send the model to the device, very important. All of the things should be sent to the device, which is the GPU device. Otherwise, some will be on CPU, some will be on GPU, then the training will not. We create the optimizer. Here we are using SGD optimizer with momentum, 0.9 momentum. We mentioned what are the parameters that I have to optimize, model.parameters. We have some learning rate schedulers also. So basically, one way to reduce learning rate is after every epoch, you reduce constant, or like with a constant term. Otherwise, you can have like different ways, like you can use more decay type of a learning rate decrease or exponential. So here we have something called as reduce LR on a plateau, one way of reducing the learning. So train model basically takes the model, all the number of epochs, loaders, everything, trains and outputs the losses, accuracies during the training and validation. And that is what happens. So you train the model for 5 epochs. These are the losses which you see, mini batch loss and the overall running average. Accuracy also, this is the accuracy. Now if you want to see the outputs, this is what we look like. So these are the 10 different classes. For cat, ship, aeroplane, frog, another automobile, truck, horse, dog. So these are the different classes that are there. 10 different classes, and P is nothing but the prediction. T is nothing but the ground. So this is one way to create your own ResNet from scratch, train it on the CFAR10 dataset. Of course, sometimes when you want to create bigger data sets, when you have bigger data sets and bigger models, training from scratch may not make sense. That is where fine tuning will help. So all the functions remain the same. The only difference in fine tuning is how can we use that pre-trained way. How do you first load the pre-trained model? And when you're updating the model also, only certain layers needs to be updated, not the entire all the layers. Only certain layers needs to be updated during the fine tuning stage. Because if you update everything, it is unnecessary. Again, it'll take a lot of time to do the entire model update. All we want to do is use that big knowledge and distill or make use of transfer that knowledge to a smaller task which only few layers can do. Updating few layers can solve that. Don't have to update the entire model. So that's what here we see. Again, I'm not talking about these helper functions for data loading, which we just discussed. Same set all seeds, deterministic, all the same helper functions which you just created. Even train model remains the same. I will directly go into how do we actually create the model. Okay. So this is where the model comes. So we first load the model. In our case, we are loading a VGG model. You can load ResNet model also. Anything is fine. Torch vision.models. This is a place where you have a bunch of pre-trained models that are present. VGG 16, ResNet 34, ResNet 50, ResNet 101, InceptionNet, TenseNet, Mobile, whatever. Even you can upload your own model also. There is a process. So all the publicly available models are present in torchvision.models. You just have to specify which particular model you want and mention pre-trained is equals to true. Then it will load the model along with the pre-trained weights. If it is false, it will load the model architecture, but the weights will be random. So this is where model is getting loaded. And if you visualize, if you print the model, this is what it looks like. So it is a sequential layers, a bunch of different layers you can see. And then after the convolution layers, you have the fully connected layers in the bottom. Now we have to first, like I said, freeze first all of the layers in the model. That is what this is saying. For parameter and model dot parameters, requires grad is basically it says whether the particular parameter needs a gradient or not. If you don't need a gradient, it means you're not updating that particular parameter. So if you're keeping param dot requires grad is false, it means you'll never update those parameters. So first you freeze the entire model, then we only unfreeze those particular layers like model dot classifier 1 and 3. These are just two layers which for which the parameter is now unfrozen. Basically we're saying requires grad is 3. You can do this for whatever layers you feel is correct. That is a again a strategy which will only be like hyperparameter optimization. You try out different values and you figure out which is the best. In this case, we're just using these two layers. One important thing is the last layer, linear layer, needs to be changed because if you have different classes compared to what this uh, pre-trained model has been trained, then the class last output layer will not be the same. For example, if the pre-trained is trained on 100 classes, whereas I have only 10 classes in my data set. So I have to remove that last layer of the pre-trained model and I have to add a new linear layer, which is now projecting into only a 10 classes, which will be the output of my particular task. So you have to always make sure that the output matches to whatever your data set has. Otherwise, it will be a big problem. So that is what we're doing. We're creating a new linear layer, removing the existing VGG16's output layer. We're removing that and adding a new linear layer to this. That's it. Once this is done, the entire again the process remains the same. Here we send the model, we have the optimizer, schedulers, send it to the train model, and we plot the loss. These are the mini batch losses. This is the accuracy. Again, if you visualize, this is what it looks like. There is also the confusion matrix for this particular task. Yeah, so that's it. This is what I wanted to discuss in today's session. Any doubts, questions, I'll be happy to answer right now. You can post in the chat or you can also unmute and ask right now. Anything in the code, anything that is not clear conceptually. If everything is clear, then Thank you all for joining. I'll stay on the call still for a few more minutes. If not, if you don't have questions, you can drop the call. Thank you all for joining. Okay, I'll stop the call for now. Thank